Okay, welcome back, everybody. So it's my pleasure to introduce Jeff Calder, who is going to do the last talk of today. It's going to be a traditional whiteboard talk, and he's going to talk about convergence rates for the Lipschitz learning. Thank you very much.
Okay, yeah, so thank you very much for the invitation to talk. So I haven't given, a talk with a chalkboard or a whiteboard in like a year and a half. So I thought it would be a good opportunity to do this now. So I'm just going to talk about some very recent work, which is joint with Leon Bungert and Tim Royth, who are both attendees here at the workshop, and we should have a preprint very, very soon on this idea. And so just to get into things, we will have a graph, which will be the central object of study, like in other talks this week. And so that we have vertices, we'll call them omega n. So this is x1 through xn, which are a subset of a domain, omega, which is a subset of Euclidean space. And we have edge weights. So these are wij between two nodes xi and xj. And this is eta of xi minus xj divided by a length scale h. Okay. So we connect points that are nearby in space with an edge weight. And so the picture for eta is that it starts off large at say 1 and then decays to 0 before you get to say 1 here. Okay? So h is the graph bandwidth. And so attached to this graph, you also have labeled data. Okay, which is a function g on a subset, I'll call it script on, into just the real numbers for now, but you can extend these things to vector valued labels. So this is some subset of the vertices in the graph. Okay. And the task we'll talk about is this thing called graph-based semi-supervised learning. Which is to extend the labels from G, or from On to the rest of the graph. So from the constraint sets to the rest of the graph. Okay. So there are lots of techniques for doing this. A lot of them have either variational or PDE formulations on graphs. So one thing you can do is to look at the minimum of some regularization energy, E, over functions on the graph, subject to the labels agreeing on the constraint set. And there are lots of different variations of this. Instead of this hard constraint, I could add a soft label fidelity as well. So there are lots of techniques like this. One such example is P Laplacian regularization. So P Laplace learning corresponds to the energy EP of U is the sum Wij uxi minus uxj to the P. And I'll put a power P on here as well. So the idea here, at least, is that I want to make sure that my label function is as smooth as possible, where I measure smoothness by this energy, and I want the labels to agree at these labeled nodes. Okay. And now there's been quite a bit of work on these kinds of models. When you have very few labeled examples, so the set script on is very small, the sort of common case of taking p is equal to 2 is quite ill-posed, meaning that p is equal to 2 is ill-posed. when the size of the constraint set is very small. And the reason sort of is because, here you would be looking at harmonic functions with, boundary conditions at on a set of very small measure, or a set that has too small measure to have any positive capacity. And so you can't attain label conditions. So you get these sort of very spiky solutions where the solution is trying to attain the labels, but also trying to be constant on the graph. And you can get very, very poor results here. And so it's been suggested, and studied by myself and others, the problem of taking much larger values of P to enforce sort of stronger regularity on these functions. And one thing you can do is you can take the limit as P goes to infinity. And that's the study of this talk. This is what we call Lipschitz learning. So in that case, the energy you get is essentially E infinity, the max of Wij. So essentially some kind of Lipschitz constant for the function. And now this is what you get if you take the power P on the weight. If you don't take the power P on the weight, then actually the weights disappear, and it's an unweighted graph essentially. Okay, so this gives you a more general setting if you take the power P on these weights. And so actually the solution to this problem, minimizing this subject to the label agreement here, is not a well-posed problem. There are infinitely many solutions. A really simple example is, here's a very simple graph. So I'm going to put a bunch of nodes back to back. I think I need 5 of them. And the red numbers will be the label constraints. So I'm going to put a 0 here and a 2 here. Sorry, a 2 here and a 2 over here as well. So these are the labeled guys. And I want to then assign labels here and here. Now this is the graph structure, so I can have edges here, 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 and here. They all have edge weights of 1, let's say. So I'm just minimizing the difference in the labels across these edges. So here I have to put a 1, right? This gives me the smallest Lipschitz constant. So that's the solution here. But over here, maybe I want it to be 2 to be constant, right? But anything between 1 and 3 will give me the same Lipschitz constant of 1 here. So the value I put here could be anything between 1 and 3, and I'm still minimizing the objective. But you want to put the value 2 here. Okay. And to characterize that solution, there are several ways to do it. So in the machine learning literature, people look at these things called Lex minimizers. Which essentially what you do is you take the gradient, which in the graph setting, the gradient's just a discrete object. It's all of the differences across edges. And for any 2 solutions, you can look at the lexicographical ordering on gradients, and you can take the minimizer which is smallest in the lexicographical ordering. And that's one way to do it. An equivalent way, which has been used in analysis for some time, is this thing called absolutely minimal Lipschitz extension, which basically says that instead of minimizing the worst case Lipschitz constant over the whole graph, I also ask that among all minimizers, I select the one that cannot be locally improved on any subset of the graph. Right, so let's see. Both of these notions are actually equivalent, and both of them give you an Euler-Lagrange equation on the graph that's nice to write down. So both AMLE and Lex minimizers solve the following graph infinity Laplace equation. So I'll write it as LH infinity of U is 0 on the graph minus the constraint set. Subject to U is equal to G on the constraint set. Okay. Where this L infinity H is the infinity graph Laplacian, which is max plus min over j of wij uxj minus uxi. How can you see this? There are several ways, but probably the easiest is to take the gradient of this, set it equal to 0. You get the p Laplacian on the graph, and then send p to infinity, formally at least. And the same way you get the max here for the energy, if you send p to infinity in the gradient of this and split the positive negative terms apart, you get exactly this over here. And now, so the question is, what do you get in this, discrete to continuum limits that we've talked about a lot in this workshop? So if I take the large sample size, so we're interested in looking at the continuum, n goes to infinity and h goes to 0 limit of this equation on the graph to understand the why this gives you a good method for propagating labels at, let's say, very low label rates. And so this has been studied in several previous papers by myself and by other people. We're giving some new insights on the convergence rates for this problem. Okay, so just to give an idea, now I'm going to see how quickly I'm going here. Now, if you haven't seen these kind of problems before, you might not see right away what the continuum PDE should look like, but it's not hard to see what one should get. So if you take, remember that we had these weights, I just erased this, but we had the weights are geometric weights. And let's just consider the case where eta is the characteristic function of the unit interval, for simplicity here. Then if you look at the max of u of y over y that are in a ball of radius h. Okay, so this is what you get here. If the weights are just 1, you're looking at the max and the min of a function at nearby points. And say we pass from discrete to non-local, so it's not a max over the point cloud, but it's a max over a ball like this now. And what you should get is that this should be roughly u of x plus h in the direction of the gradient. Okay. And of course, if you take the min, you should get the same thing, but with a minus sign here. So if I write down the graph infinity Laplacian at xi, what I should get is a term like this, let's just write x instead of xi. Plus h grad u over norm grad u. I should get that plus a term like x minus h over this, and then minus 2 u of x. Right, because I'm not optimizing over the xi. The u of xi is just fixed, and I have 2 of them from the max and the min. So this looks essentially like a second derivative estimation, right? So for the second derivative in the direction of the gradient. So this should give you approximately h squared times grad u over norm grad u, Hessian of u, grad u over norm grad u. And this thing is what we call the infinity Laplacian of u. So it's the second derivative of u in the direction of the gradient. And that's the equation that you should get in the continuum limit of this guy here. Of course, this is in a very simple setting where the weights are the characteristic function of an interval, but you can extend these arguments to more general settings. Okay. So to write down the continuum problem, and feel free to ask questions throughout the talk whenever you feel like it. You should have infinity Laplacian of u is equal to 0 on the domain omega. So to draw a picture, I have this domain omega, and I have these points that are in my graph, but I also have special points that are labeled, which are the red points, let's say. Okay, that's the constraint set. And the setting will be that this is sort of a finite collection of points that are converging to a finite collection of points, script O in the continuum. And so I'll have the Dirichlet condition on this set O, let's say. So we'll have to have in some sense that ON converges to O. And what you should get is the natural Neumann condition, which is the natural variational boundary condition on topological boundary of omega. So this should be our continuum problem. But there are actually several ways to equivalently interpret this problem. It's a good question. So you can see it through a limit of, say, P Laplace equations, P goes to infinity. So if you were to say, look at the Dirichlet problem, minimize integral of grad U squared, right, over a domain without boundary conditions, you would get the Neumann condition. It's a natural variational condition. You would get the same thing if this is a power P for finite P as well. And so if you send P to infinity, you would expect to get Neumann condition as well. Actually, it's a little difficult to establish well-posedness in general for here. So the best that we can figure out is that if omega is convex, you can get well-posedness for this equation. But what I talked about with the AMLE, the absolutely minimal Lipschitz extension, this stuff carries over to non-convex domains and so on. So there's the equivalent AMLE interpretation of the continuum problem, which is the same as what's on the graph. I didn't write it for the graph, so let's write it for the continuum. It says that essentially for every set V compactly contained in the closure of omega, we have that the Lipschitz constant of U on V is the same as the Lipschitz constant restricted to the boundary. So it's essentially the optimal extension on any subdomain as well. You have to interpret, for the Neumann condition, you have to interpret the boundary as the relative boundary in the induced topology on the closure. So it doesn't include the boundary of omega in here. And this is some small technical points. Okay. And there's a third thing called comparison with cones, which I won't write down now, but if I have time to write down a very short idea of a proof, you will see this thing show up. And these are actually three equivalent ways of looking at the continuum problem if omega is convex, whereas AMLE comparison with cones are equivalent and more general in the non-convex setting as well. And let's say, we're not sure that you can't establish well-posedness here for non-convex domains, but it seems challenging, and it seems to be open as far as we are aware in the PDE literature. Okay, so now what can you say about the continuum limits here? So we have our continuum model, we have the discrete model. So I'll give you an older result. So this is just sort of an informal theorem statement. This is from the thesis of Charlie Smart in 2010. It's in a more special setting. So it's that omega is a grid in dimension 2, spacing h. Eta is the characteristic function of the unit interval. And in this setting, so he proved that un minus u is less than a constant third root of delta n over h squared. I'll say what these things are shortly. This is for h much less than delta to the 1 over 5. So delta n is the resolution of the point cloud. Okay. So essentially, I'll write it as the Hausdorff distance of omega n to omega, plus we'll also have an term to control the convergence of the constraint set. So basically, how far do I have to move points in omega to find the closest point in omega n? Okay. Now, so this kind of result, okay, it's specialized in various ways, but it's not so important that it's a grid or that you're in dimension 2 for the techniques they go through for a graph and more generality. But as far as we can see, the choice of eta actually is a little bit important for these techniques. And then there's a theorem in a paper that I wrote in 2019, which operates in the full graph setting with general kernels, but worked on the flat torus to get rid of this boundary condition. And sorry, yeah. UN is the solution of this equation. Thank you. Sorry. Solution of this equation up here. Thanks. Okay, so it's the solution of the discrete graph problem with n points and with a length scale h. Okay.
UN minus u refers to the.
It's the absolute difference over the graph. Yeah.
Okay.
So if you restrict the function u continuum problem to the graph and look at the absolute difference, take the max over the graph. Yeah. Grid. Yeah. Sorry, sorry, omega n. Omega n is a grid of spacing h. Sorry. Thank you. Please, ask questions like this. This is very good. Oh, so actually, I forgot to mention as well. So in Smart's work, it's not really the Neumann problem. So here, his constraint set is a tube around the boundary. So it's really the Dirichlet problem in this setting, and then it can be arbitrary boundary values. Okay, so this is quite an informal result because it's not in the same setting that I'm talking about. But the idea is, we use a lot of ideas from this work.
To obtain the well-formed what kind of solution we
on this set. This is not so important. So in our work, it's just a finite collection of points because the solutions are Lipschitz in this case. The geometry or conditions on the constraint set are not so important. Yeah.
So if you look at the sequence of minimizers for the P Laplace energies,
yeah,
does that select the AMLE of the continuum of minimizers that you've got?
It does in the convex setting. I would suspect it does in general. I'm not sure if we have a proof of that. Yeah.
Thank you.
Okay, so the other result to say, so this was in a paper I wrote recently, somewhat recently, is there's no convergence rate, but the condition on H is better. So UN converges to U for H much bigger than delta n to the 2/3. Okay. So implicit in this kind of rate is that H is much bigger than square root of delta n, or else the rate becomes vacuous essentially. And when you're working with graph-based learning, you actually want to work at length scales h. The h is the graph bandwidth. You want to work with length scales h that are very close to delta n. Okay, so essentially the graph is connected for h bigger than a constant times this delta n. And in practice, you usually work pretty close to this graph connectivity threshold. So you have very, very sparse graphs. Okay. And the sort of existing theory for convergence rates is lacking in this regard because you have these very large length scale restrictions on H, which are not something you would see in practice ever. And so the motivation for this work is to see if you can push these convergence rates down to the graph connectivity threshold at very, very small values of H. There's a work in this direction by Bungert and Royth, where they proved gamma convergence for the discrete problems to continuum when we're just above the graph connectivity threshold. And this is a recent paper in 2020. It's sort of somewhat tangential to this discussion because the gamma convergence doesn't detect absolutely minimal Lipschitz extensions. And so you can't, as far as we can see, you can't directly get from this that you have convergence of absolute minimizers. So let me write down our result. So this is our theorem. Okay, so our rate un minus u is now the fourth root, but what you see here is just delta n over h. And this is for delta n much less than h, less than delta n to the 5/9. Okay. And we do have a rate in the larger, I mean, this is what we're sort of interested in, is these very, very small length scales, but we do have a rate in the larger length scale regime, and it's just h to the 1/5. So when you contrast it with the rate from Smart's work, the difference is we've improved the denominator to h instead of h squared, but you lose this extra root. So from the cube root to the fourth root here. But you can see in the rate, all you need is delta n much smaller than h in order to get a non-vacuous rate.
Setting the same as the first what we had, the eta is
general eta. Yeah. So just decreasing upper semi-continuous, compactly supported. Yeah. Okay, so I hope to tell you a little bit about the proof of this. Okay. And I think that the ideas are quite general, right? And so there are more problems than just Lipschitz learning where you can't get to these very small length scales, and we'd like to address these problems. And even though these ideas are kind of, in some sense, special to the infinity Laplacian, the main idea, I think, will apply to other problems just with sort of completely different ingredients. And so the idea is that if you look at this infinity Laplacian, you know, in these discrete to continuum problems, you always pass through a non-local problem. And we've seen this in other talks in this workshop so far. And usually you pass to a non-local operator that has the same bandwidth. And you're just sort of replacing sums by integrals or so on. So here you would replace the max over the point cloud with the max over the domain. Instead, we're going to pass to a non-local operator on a much larger length scale. Where epsilon's much bigger than h. And this will be essentially some homogenized operator where the weights will now appear in just a constant up front and not inside the operator itself. And so this operator is easy to write down. It's in lots of other works as well. So this operator is the infinity Laplacian, the sort of non-local version of it, which is max plus min. This is over a ball. So both are over the ball of radius epsilon around x of u minus 2u of x. I write b sub omega because this is a small thing that there isn't time to explain in this talk too much, but we have to use geodesic balls. So we measure the distance between points by the shortest path in non-convex sets. Okay. So most things, distances and balls are all geodesic balls. So this is our non-local operator. You don't see the weights in the graph anywhere in here because they've been homogenized into this constant. And so eta is the only place where the kernel shows up. Where can I write it? So eta is our sigma eta is the max of t eta t. This is the only place that you see the kernel showing up here. And so this idea of passing to a non-local operator on a larger length scale, I think is a general idea that could work for other problems like spectral convergence. And if I have time, I'll talk about ideas for that at the end. But of course, the ingredients will be much different than in this talk. And so the idea is when you pass to this larger length scale, your length scale restrictions now involve epsilon instead of h. So you can work with a very, very small h in the graph and a much larger length scale epsilon. Okay. So the exact form of what does this mean here? Is what I would call discrete to non-local. And so what we prove is, well, first we have to have a way to interpolate the function from the graph to the domain. And because this is the infinity Laplacian, there's a very special way to do this. So the function un on the graph, I extend it to the continuum. I'll call it un epsilon by taking the max of u over balls. Okay, we'll have to do the inf version of this as well. Okay, so this is a way to extend un from the point cloud to the domain. Okay. And the result for discrete to continuum is that if I have a subsolution on the graph, right? So minus Laplacian of un is less than or equal to 0. Of course, it's equal to 0 if it's the solution, but you need just the subsolution condition. Then minus non-local operator applied to this extension is close to 0, okay? Approximately 0. So you get delta n over h epsilon plus h over epsilon squared. And in some sense, this term here, you should kind of think as playing the same role as this term in Smart's rate, but we've decoupled the h and epsilon, so one of the h's became epsilon. So you have this discrete to non-local. So you take the discrete function, extend to a non-local one that approximately solves the non-local operator, and then you have also a local to non-local. So oftentimes you sort of always pass to the local problem and do everything here. In this setting, we sort of meet in the middle. So we take the discrete to non-local, but we also take local to non-local. Everything meets in this non-local problem, okay? And we do the bulk of the argument here. So here we're going to take the continuum thing and do the same kind of perturbation. So u epsilon is the max over balls. Sorry. And u sub epsilon is the min. Okay. And okay, so this local to non-local, it's not a new thing in our work. So this is the same thing that Charlie Smart used in his work. Which, by the way, this was basically, I think, only in his thesis. We couldn't find anywhere where he had published this result. So I think it ended up only in his thesis dissertation somehow. So what's really amazing here is that the continuum guy here, if I take this min over balls, then minus non-local Laplacian of u epsilon is bigger than 0. It's exactly bigger than 0. Okay. So I can take the solution of the local equation and I can plug it into the non-local equation and get exact satisfaction here. This is something you never see in these sort of non-local to local problems. There's always like a Taylor expansion going from here to here, and you have Taylor expansion errors and so on. And so it's quite miraculous that you can do this without any errors here. And this is completely fundamental to getting the rate in these problems. So once you have these two things, then you apply the comparison principle for the non-local equation to relate u epsilon to un epsilon. And that's where the rate comes from. So if you apply the comparison principle, for the non-local equation, this gives that, so this is a subsolution property, supersolution property. So you get un epsilon minus u epsilon. So there's a couple of tricks you have to play here. So you get a cube root because of them. So you get this, So essentially, this is not a subsolution relative to that because this thing is positive, that's 0. You have to make a perturbation trick. You have to take this super solution, perturb it to be a strict super solution, so it's larger than this right-hand side. That perturbation trick is very non-trivial for the infinity Laplacian, and the ideas are contained in Smart's work. And when you do this perturbation trick, you lose a little bit, and so you get this cube root of this difference here. Yeah. And now, of course, you can remove the epsilons. Everything is Lipschitz. So you can remove the epsilons. And what you pay is just an epsilon cost here. And then you optimize over epsilon. And that gives you these results in these different parameter regimes. Yeah. And so let me say, I want to say a bunch of stuff, but I don't know how much time I have. Okay. Yeah, sure.
This is because you're in this special solution, the AMLE.
Yeah, so this uses actually the, well, AMLE, but really it uses this comparison with cones that I'll talk a little bit about. Yeah. Yeah, and that's crucially used in this argument and this one as well. Yeah. Yep. Yeah, it's used to get the discrete to non-local. In the graph setting, it's used for local to non-local in the continuum setting. Use both these ideas. Yeah. So because I only have a little bit of time, let me just, it's like 3 lines to show how you get this local to non-local. Let me show you how this works. And then the graph setting is a similar thing, but you replace everything with graph analogs, essentially. So the proof of this, call it star. Okay, so the first thing is I claim that u of y bigger than u of x plus u of x minus u2 epsilon x over 2 epsilon. Okay, I claim this is true for y in the 2 epsilon ball around x. Okay, so I have to wave my hands a little bit to get this. And there's, of course, this is minus here, sorry. So the way this works is that you use this thing called comparison with cones, which is actually quite simple. So the observation is that the infinity Laplacian of the cone function is 0 for y is not equal to x. So cones are actually infinity harmonic. Why is that true? It's very simple. It's just a cone in the direction of the gradient, it's linear. So its second derivative vanishes, right? The infinity Laplacian is just the second derivative in the direction of the gradient, okay? So cone functions are infinity harmonic. And so I can apply the comparison principle between my infinity harmonic function and this cone function. And to prove this, all I need is that this inequality holds on the boundary of the ball. And then it has to hold inside too by the comparison principle. On the boundary of the ball, the x minus y and the 2 epsilon cancel, and the ux's cancel, and I get exactly uy is bigger than u2 epsilon. That's the minimum over the ball. Okay, so it holds in the boundary. The other part of the boundary is the center of the ball, because I'm not infinity harmonic there. At the center of the ball, where x is equal to y, that term's gone, and y is equal to x. It's trivial as well. Okay, so it holds in the boundary. It holds inside by the comparison principle. This is a relatively smooth function. You can prove this comparison with cones without any complicated viscosity solution machinery. It's almost like by hand you can prove this. I lied a little bit because we have to use, in place of cones, we have to use geodesic distances on the domain because we have this Neumann problem. Okay, but I'm going to wave my hands around that stuff. Now I simply minimize over the ball of radius epsilon on both sides. Okay. Minimize over this ball, and this will be in the worst case epsilon, so I get a 1/2. Okay. And in the end, you get U epsilon, which is the min over that ball, is bigger than a half U plus U2 epsilon. So you get this just by minimizing this over the epsilon ball. And now I write down the infinity Laplacian of U epsilon, okay, at X. Remember, this is the max plus the min over the ball. And it's U sub epsilon and minus 2 U sub epsilon of X. Now, essentially, okay, it's just one line here. So when you take the max over the ball of the min over the ball, it's less than U, you could prove, okay? When you take the min over the ball of the min over the ball, you get the min over the 2 epsilon ball. Then you get minus 2 epsilon. And that's less than 0 by this right here. Okay, that's it. Okay. So it's this comparison with cones that gives you this local to non-local in almost no work. And this is not new to us, just to be clear. So this is all, in a paper by Smart and Armstrong, based on Charlie Smart's thesis paper. So our contributions here are really in the discrete to non-local. So it's the same comparison with Cohen's argument, but just to say in words, you have to write down what's the right notion of these cone functions on the graph. Okay, so they're solutions of iconal equations on the graph. You have to show that they're infinity harmonic on the graph. They're actually not, they're subharmonic, but that's fine for the argument. I only need one direction here. And so you can prove comparison against discrete cones for this guy. And then the proof reduces to convergence of the cone functions in the graph. These are first order equations, iconal equations on graphs. And it's much more straightforward to prove convergence of these distance functions or cones on graphs than it is to prove convergence of the infinity harmonic functions on graphs. And this makes a lot of sense because you're looking at Lipschitz extensions, and the cones are the iconal equations on graphs. They describe the metric on the graph. And if the metric is converging, you should have convergence of the absolutely minimal Lipschitz extensions as well. Okay. So I will stop the proof there, but I'll just say a couple of things about extensions of this idea. Right. So really what we'd like to do, actually this is where I started with this project, and I wasn't able to solve this problem, so we tackled this one instead. What I'd like to do is to look at spectral convergence, which I've written some papers on recently. So this is if I have an ordinary graph Laplacian, and I have an eigenvector eigenvalue for this, and I want to have convergence to a continuum eigenvector eigenvalue problem. There's a lot of papers recently on convergence results in this setting. There's recently a paper by myself and Nicholas Garcia-Trilos and Marta Lewiska, where we showed L infinity convergence rates of order H in this setting. But there's a length scale restriction, like I told you before. So this is delta n to the d over d plus 4. Where delta n is not the exact same thing I wrote before, but it plays a similar role. So it has the same scaling, essentially. And you'd want to prove these convergence rates all the way down to the graph connectivity threshold. There is quite a bit known down to that threshold, but the rates are not strong uniform rates. So you can use the gamma convergence framework of Dan Slepchev and Nicholas Trilos to push these convergence rates down to the graph connectivity threshold, but you get worse rates that are in the L2 sense and not in the L infinity sense. And so if you want these improved rates, you need some way to get convergence of the operators down to this length scale. Okay. And to say a word about how you can do this, I think it's the same idea I talked about, passing to a non-local operator on a homogenized length scale. Okay. And what you can do, let me just write the formula here, is that if I take a random walk on the graph, maybe this isn't the best place to write things. right over here. So take a random walk on the graph. I won't write down the transition probabilities. It's the usual one defined by the weights in the graph. Then if I have an eigenvector problem here, if this is the random walk graph Laplacian, then I can write u of x as the expectation of u of xk along the random walk, 1 minus lambda minus k, given that I start the walk at x. And I would call this a Feynman-Kac formula, Katz. And you can, you should have small eigenvalues, large k. You can Taylor expand this kind of thing. 1 plus lambda k, like this. So say x to denote that I'm going to start at x. And so what you get is, I would call this a homogenized eigenvalue problem. Lk of u is equal to lambda k expectation of u. And so of course this expectation is over the random walker, not over the random graph that we're constructing and so on. So this operator Lk of u is the difference between u and expectation of u over the random walk. Okay. It's Laplacian because it's a difference between u and its average locally. Okay, this is how you should think of a Laplacian. And the length scale, right, should be, this is the role of epsilon from our work. This should look somewhat like the sort of the set on which, or the diameter of the set on which the sort of bulk of the heat kernel is concentrated, which is square root of k times h. So you get this larger homogenized length scale. And then over here, this condition should become something like square root kh is bigger than this. And so if you take k large enough, you can get by with much smaller values of h, we think. But this all boils down to getting a consistency estimate for this homogenized graph Laplacian operator. If you want to know that this thing is consistent with your differential operator in the continuum, I think this is a hard problem at small length scales, as far as I've seen so far. Okay, so it understands it would require having very, very detailed knowledge of the heat kernel on a graph at these very small length scales where this is hard to obtain. I think it's maybe similar to some kinds of supercritical percolation problems and so on. But this is essentially the kind of things that I'm thinking about at the moment. And I think I will stop here. I'm happy to answer questions.
So is there any questions, more questions or comments? Okay, 1 second.
Right. So if we, thanks for a wonderful talk. Okay, now it's on. So on the right board, you had those rates, right, in these two regimes when h is small and h is big. And if I did quickly, right, kind of it seemed to me that the best thing that you can get is the conductivity length scale to the power 1/9 as your optimal rate on the right-hand side, right? Yeah. So what is that you expect? I would guess linear, right?
In the conductivity scale?
Yeah, well, right.
Yeah.
Kind of for what is the best rate that you expect in general over the right side? Is there any reason to think that it's going to be less than linear, right? Less than first order, right?
Yeah, so I don't have any reason to believe that what we've done is optimal in any sense.
Yeah, no, yeah, right.
Yeah. You know, we haven't done enough experiments to sort of check this yet, and it seems a little difficult. I think essentially, you know, we do think that this condition, you know, right over here, that h is much bigger than the graph conductivity threshold. We do think this is essentially necessary. So I don't think you're going to get convergence at smaller length scales like you do in some gamma convergence problems. And the reason is that you can, you know, your metric's not going to converge if you say have a grid and you're forced to go along a staircase path between 2 points, you're going to have a square root 2 factor difference in lengths and so on. So you do need this kind of condition, right? So you're not going to get delta n all the way down to graph conductivity, let's say. But I would expect to get much better than delta to the 1/9 I don't have any intuition about what it should be.
Well, although,
The
so
optimal,
just to make a comment, I believe that even if you go down below, right,
Yeah.
you would probably, kind of there are these results on homogenization of the lengths, and you could probably show that what you're getting is a constant multiple, right? There is a
Yeah.
homogenization of the, right, and you would probably still be able to relate the solutions up to some constant factor, right? Okay, that's another problem,
Possibly.
right? Yeah, thanks.
We can talk. Yeah.
Lorenzo?
Right, to talk about that.
Better
Okay, perfect. Very interesting talk. Really like the intuition behind the proofs. I'm just curious about this trick you were talking about, like meeting halfway in the non-local setting. Aside the specific rates of convergence, do you think something like this can also be done for P, not only for the infinite Laplacian?
This is a good question. So it's much harder actually for the P Laplacian. As far as I know, I mean, so people study these non-local equations, right? So this non-local equation, which is also one for the P Laplacian, not the usual variational P Laplacian, but this thing called the game theoretic P Laplacian. The non-local equations are studied by probabilists and PDE people because they have stochastic tug-of-war game interpretations, which can be done on graphs or in a non-local domain. And in that community, as far as I know, it's an open problem to get a convergence rate for the P Laplacian, P is not 2 or infinity,
Right.
to get a convergence rate from non-local to local. This is an open problem because essentially you have sort of no business getting rates anyways because the solutions are not smooth. So you don't have smooth solutions. You know, it's somehow miraculous that you get a rate for the infinity Laplacian.
Right. Of course, the U and epsilon, I guess it should be some sort of, I don't know, convolution type of things in the non-infinite regime, right? I guess this choice of the max is really
yes, absolutely.
like tailored to the infinite Laplacian, right?
This is absolutely tailored to the infinity Laplacian. I don't think you would use the same thing for the P Laplacian for sure.
All right, very interesting.
Yeah,
Thank
yeah.
you.
Yeah, I would think something like, you know, this is what's done in like the gamma convergence, is it's some kind of nullification on some very small length scale, right? And, you know, maybe the same thing would work for the P Laplacian. I mean, I'm sure it would. I think probably in Dan's paper with Matt Thorpe and so on, they use a similar convolution for the P Laplacian. But in terms of the convergence rate then, you know, so I mean, going from discrete to non-local might not be so challenging, but it's more like the going from local to non-local, right? Which you would normally need regularity for that. Going local to non-local, you would Taylor expand and use regularity to get this. And in the P Laplacian or infinity Laplacian, you don't have that regularity. You would need like C2 alpha or something. You don't have this. And there's this like miraculous comparison with Cohn's thing that gives it to you for the infinity Laplacian.
There's no like P Laplacian
What the cones should look like. Well, I mean, there are like the you know the cones look like they're fundamental solutions for the P Laplacian. So they look like x to the p minus d over p minus 1, I believe, if p is bigger than d. So these Holder cones. But as far as I know, it doesn't characterize solutions of the P Laplacian. These actually characterize. So if your function satisfies comparison with all cones on all subsets of the domain, it's a unique way to characterize the solution of the continuum problem or the AMLE. Okay. And that's, as far as I know, specific to the infinity Laplacian. Yeah.
I would ask a question or make a comment.
I want to make a small comment regarding Dejan's question on how sharp the rates are. I mean, there's one way to improve the rate a little bit, namely by assuming that the solution has positive gradients everywhere. This is a trick which is also done in smart thesis. And this basically shows that our rates are really worst case rates, because if there's one single point in the domain where the gradient is 0, then we will have this deterioration of the rates. So you can play with that in order to improve them. And then there's another thing, namely we extend our graph solutions to the continuum domain and then show rates for this extension. And this gives us this additional term of epsilon. And we sort of suspect that if you were just interested in rates on the graph, then you might actually be doing much, much better. Yeah. But this is sort of then a different technique than what we did.
Yeah, very good points. Yeah, it's that cube root thing that I talked about, right? this doesn't show up. If your gradient never vanishes, your solution, then you can get rid of the cube root. Okay? And it's somehow like when you make the perturbation from subsolution to strict subsolution, you need a non-vanishing gradient for this, and there's an extra perturbation trick to get to that non-vanishing gradient, essentially.
Okay, other comments, questions? So if not, let's thank again Jeff and all the speakers of today.